A conducting rod, it's this guy over here, with a length of 0.25 meters makes contact with two conducting and parallel rails. These are the rails here, and they go out in that direction. And they're hooked up to a resistor here. A constant force F moves the rod at a constant speed of 3 meters per second to the right. Okay, that might set off some bells right now. How can a force have zero acceleration? Well, there's going to be a force from the magnetic field in the opposite direction that will balance it out. The apparatus is placed in a uniform magnetic field of 2 Tesla that is perpendicular to the rails and the rod and into the page. That's all these X's here. Calculate the magnitude of the induced EMF in the rod. Find the direction of the induced current in the resistor. Okay, they're not asking for it through the rail this time. They're asking for it through the resistor, or through the rod or the rail for that matter. Calculate the magnitude of the induced current in the resistor. Calculate the power dissipated in the resistor during the time when the rod moves in the field. Then, calculate the external force necessary to move the rod at a constant speed through the magnetic field. Calculate the magnitude of the induced EMF. We derived this equation earlier in the chapter, and it's magnetic field times length times velocity, or BLIV. So we have 2 Tesla, and we need this length here, which is 0.25 meters, and we're going at 3 meters per second, so we get 1.5 volts. Handy equation to know. Find the direction of the induced current in the resistor. That's this guy right here. Well, as this rod goes down the line, what's happening to the flux within the area enclosed? Here's your circuit. That's where current is flowing now. The flux is increasing into the page. So, Lenz's law, you have to induce a current that opposes that increase in flux. So you're going to want to have a magnetic field coming out of the page. So if we grab the rod here, like this, there's the fingers, the thumb, wrap the fingers around the wire, you will see, hopefully, that gives you a magnetic field out of the page. So you might just say, okay, so the current's going up. We're not asking for that. We're asking for the current through the resistor. So you follow it up like that, comes down through the resistor. And good. There we go. Calculate the magnitude of the induced current in the resistor. Well, current, Ohm's law, just V over R. Our voltage is 1.5 volts over 2 ohms, and we get 0.75 amps. Calculate the power dissipated in the resistor. And what's going on there? The resistor is heating up, and your electrical energy is being converted into thermal energy. So we use P equals IV, and we have our current, we have our voltage, and we get 1.13 watts. Calculate the external force necessary to move the rod at a constant speed through the magnetic field. Well, we're going to use the equation for the force on a rod moving through a magnetic field. That's the force created by the current flow and the external magnetic field. So let's take a second. We said the current's going in this direction. So now we have a current going through this wire up. The magnetic field is into the page. Use the right-hand rule, not the right-hand grip rule, but the right-hand rule, and you'll find that the magnetic force is in this direction. That's opposing the motion of this rod. So if you want to move the rod at a constant speed, that's zero acceleration, right? So you have your applied force, and let's say positive is to the right, minus the magnetic force has to equal zero acceleration. So once we find the magnetic force, we found the external force. So the equation for the magnetic force is current times this length here times the magnetic field, put in our variables, and we get 0.375 newtons, and that's the force we need to apply to move it at a constant speed.